Welcome back. In this video, I'm going to go over Lagrange multipliers. Let me give motivations. One of the many challenges in economics and marketing is predicting the behavior of consumers. Basic models of consumer behavior often involve a utility function that expresses a consumer's combined preference for several different amenities. So for example, simple utility function, the U defined by f of L comma G. So here L represent the amount of leisure time and G represent the number of consumable goods. The model assumes consumers try to maximize their utility function, but they do so under certain constraints on the variables of the problem. For example, increasing leisure time may increase utility, but leisure time produces no income for consumable goods. Similarly, consumable goods may also increase utility, but they require income, which reduces leisure time. So the L and G, as you can see here in the graph, L and G, it has inverse relationship. So the goal in this video, the goal is to develop a general method for solving such constraint optimization problems. So here's a basic idea. Before going over basic idea, let me review the theorem 1, what we saw in the directional derivative and gradient. So let f be a differentiable at a comma b with gradient f is not equal to 0 vector. And then first statement, f has its maximum rate of increase at a comma b in the direction of gradient of f, and the maximum of the directional derivative is absolute value of the gradient. And the second statement, f has its maximum rate of decrease at a comma b in the direction of gradient of negative gradient f. And then the minimum of directional derivative is negative absolute value of gradient f. And third statement, the directional derivative becomes 0 if the direction vector is orthogonal to gradient f. So please keep in mind this one. So now what you're going to do, think about this kind of the surface, okay, and then we seek maximum and minimum values of differentiable objective function of that graph. Z equals f of x comma y. This is a multivariate function of that surface, okay, with the restriction that x and y must lie on a constraint curve C, defined by g of x comma y equals 0. So which means that g of x comma y equals 0, this is the graph of g of x comma y equals 0, which is a curve. So the domain of that function is on this curve. Okay, so we have to choose x comma y on that curve for that function. Okay, so in that constraint, we want to find out maximum and minimum of function f. Okay, so that's the basic model of the constraint optimization problem. Okay, so now then let's think about some more simpler the situation. So here we assume the level curve. So you see that here the multiple circles. These are the level curve of the surface function f, have an increasing z value moving away from the origin, right here, origin here. So that is the smaller, the inner circle, the inner circle, the z value must be less than the the outer the circle. See, this is a level curve with z value. Okay, so then that's the curve C g of x comma y equals 0. Okay, so now then let's just pick the let's figure out gradient f and gradient g. Okay, so and for example, at this point, gradient g must be orthogonal to the tangent vector. See here the tangent vector of the curve C. This is constraint to level curve C. Okay, so the gradient, as you can see, the gradient g is the perpendicular to the tangent vector at this point. Now, what about the gradient f? The gradient f is what must be the orthogonal to the tangent vector of the any level curve, right? So it's next level curve, and then that level curve. Every single level curve, I mean for all level curve, gradient f must be orthogonal to the line tangent to the each level curve. So that's why directional gradient f like this. And then as you move the point right here P, then gradient g and gradient f is parallel because their directions are same. Okay, they have the same direction. I mean, why? Because the point P is not only on the curve but also the on the level curve of function f, right? So here we can have two observations. The first one, f has a local extrema at P on the constraint curve. The second statement, as I told you, gradient f is parallel to gradient g at P, which means that gradient f can be expressed as multiple scalar of a vector gradient g at P. Okay, so that's by the way, why does gradient f the magnitude of gradient f has the maximum value at point P? Because the gradient f, if the directional derivative direction vector in the directional derivative is the same as the direction of gradient f, then the directional derivative has a maximum value. That's what theorem 1 says right here. So f has its maximum rate of increase as in the direction of gradient f. So if the direction of the gradient directional derivative is equal to the direction of gradient f, then direction gradient f has a maximum value, so that the direction derivative has the maximum value. That's why gradient f is magnitude of gradient f is larger than the magnitude of gradient f at other points. Okay. So here's the theorems. That's the theorem is written based on the observations. So assume f has a local extreme value on C at a point P, a comma b. That's the coordinates of point P. Then first statement, the gradient f is orthogonal to the line tangent to the constraint level curve C at point P. The second statement, gradient f can be expressed as the lambda times gradient g at a comma b, which is scalar multiplication of the gradient g, which means that gradient f is parallel to gradient g at point P. So that lambda is called the Lagrange multiplier. Okay, so I proved this one, that theorem in other video lecture video. Okay, please watch that video if you are wondering the proof of the theorems. So okay, so let's just offset those theorems. Okay, so keep in mind this. If you want to find out the local extreme value of function f on on a constraint level curve C, then the gradient in that point, if the function have local extreme value at the point P, the gradient f must be orthogonal to the curve C, and then probably there exists lambda. so that lambda f is equal to lambda times gradient g. Okay, so but before so yeah, we're gonna look at the example, but before doing that, the we can classify the type of the constraint level curve C. Okay, so we can think about three cases of the constraint level curve C. Case one is the curve C is bounded and closed on itself. Okay, so the close means that endpoint is equal to a starting point is equal to endpoint. Okay, so that definitely this is a bounded and closed, right? So then in this case, the absolute extrema of function f among the local extrema, which means that you don't have to find evaluate function f at the endpoints. Okay, so then the second case, the bounded but not closed on itself. So this is bounded, but you see that starting point and then the end point is not connected. So in that case, you gotta evaluate endpoint function f at endpoints to find out absolute extrema. Okay. Last case, there's no end and then no endpoints. This is a parabola or a line. These are examples of unbounded and not closed on itself. Then we cannot guarantee that the existence of absolute extrema. Okay, so then we see the two steps for finding absolute extrema of function f on a constraint level curve C. Okay, so that's the steps um, for solving constraint optimization problems. Okay, so but we assume that the constraint level curve is closed and bounded. Okay, so step one, we find the we find x comma x and y and lambda such that lambda f is equals lambda times gradient g and g of x comma y equals 0. Okay, so which means that lambda f is equal to lambda times gradient g. What does that mean? Which means that the pair of the coordinates must be equal. So partial derivative x with respect to x must be equal to lambda times partial derivative of g with respect to x. And then f sub y is equal to lambda times g sub y, and then g of x comma y is 0. So we got three equations. So this is system of three equations, and then we have three unknowns, right? So it's solvable. Step two, evaluate f at the value x comma y found in step one and at the endpoints of C. This is literally the same same step as what we saw for finding absolute extrema of one single variable function f. Okay, so step two, we find simply we evaluate function f at the values what we found in step one, and then we evaluate f at the endpoints, and then we select the largest value and the smallest value. Okay, these are going to be absolute maximum and minimum respectively. Okay, so here's an example. Find the extrema of f defined by x squared plus y squared equals 2. So that's going to be paraboloid. The graph of f, surface of f must be the paraboloid, where x comma y is in the set in the constraint level curve C defined by x squared plus y xy plus y squared minus 4 equals 0. Okay, so this is the equation of ellipse, by the way. Okay, so this is graph of surface of the f parabola like this. Okay, it should be up to above the 2 unit above the xy plane, right? Okay, and then that's the constraint level curve C, g of x comma y equals 0. Okay, then the let's just imagine the curve on the surface whose projection is the constraint level curve C, then the probably the graph, curve is like this. The curve is must be like this, so that whose projection is the C. Okay, so then as you can see that at this point and those 2 points, f has maximum value, and then in those 2 points, see right here, and this one, and those 2 points, the f has a minimum value. Okay, then we draw the level curve on the surface of f. Just touch the the pair of the maximum the points, pair of points where f has maximum value, and the pair of the points where f has minimum value. Okay, so then if you just look at the this graph on the top, then we see this one. There are two level curve, and then that one, which is when you look at this one in the top graph in the top, then that graph will be like this, which is a constraint level curve C. So C is like this. So the extrema of f occur at point C where the level curve is tangent to the constraint curve. Does it make sense, right? So that's why I told you this if level curve touch the constraint C, touch the level curve, then that point is where f has extrema. Okay, so now it makes sense, right? Because when you in that graph, you see that what makes the point P is to be special, because the end point P, that's the point not only on the constraint curve but also level curve f. In that situation, the gradient f is parallel to gradient g, and then gradient f has the maximum, the magnitude. So, and then f has a local extrema at point P in the constraint curve. So that's why you see right there, right here, the those points are not only on the constraint curve, but also level curve of function f. Okay, that's why the function f will have extrema at those points. Okay, so let's figure out the absolute maximum minimum algebraically. So gradient f is going to be this, gradient g is like this, right? Because just find out partial derivative with respect x and y respectively. Okay. All right. So now then we will get we build what? Yeah, we're gonna get the three equations, right? Okay. So establishing the system. So f sub x is equal to lambda times g sub x, and then f sub y is equal to lambda times g sub y, and then g of x comma y equals 0. Then we got this. Then using the subtracting second equation from the first equation, we got this, right? And then simplifying this, we get this. Then we have two, we can find out two solutions in that equation, x equals y or lambda equals 2. Okay, so let's think about the first case, second case for each. First case, x equals y. Then we plug in y into x in the third equation. This is the g of x comma y, right? Equation of the constraint curve. Okay, then we got this, then we got this. Since x equals y, then what? So we got 2 points. Okay, these are candidate where function f has extrema. Okay, and then when lambda equals 2, second case, substituting lambda equals 2, okay, into the either first or second equation, we get this, x equals negative minus y. Okay, so we plug in negative y into x in the equation of curve. Then the g of x comma y simplifies this. So we got another 2 points. So these are candidate points, the points where f has extrema. Okay, so we evaluate function f at those 4 points. So we got this. Then what? And then since this is the constraint level curve C is bounded and closed, we don't have to evaluate function f at the endpoints. Actually, there is no endpoints, right? So we compare those 4 values. The largest one, we find the largest, we select the largest one and smallest one. These are absolute maximum, minimum, right? So absolute maximum f on C is 10, minimum of f on C is 14/3. Okay, so that's for today.